Let's sketch the graph of the polynomial f of x is equal to x cubed plus 6x squared plus 9x. We'll start by looking at the domain. Because our function is a polynomial, its domain is going to be all the points from minus infinity to infinity. Now let's think about intercepts. I think it's always easiest to find the y-intercept first. So to find the y-intercept, all we're going to do is we are going to set x equal to 0. And looking back up here at our function, that gives us that f of 0 is equal to 0. So our intercept is 0, 0, which is the origin. And that is our x and y intercept. Let's now look at the symmetry. To find the symmetry, what we're going to do is we're going to calculate f of minus x. So wherever we have an x in our function, we're going to plug in minus x. This gives us a minus x cubed plus 6 times minus x squared plus 9 times minus x. This is minus x cubed plus 6x squared minus 9x. If we compare this to our original function, it is not the same, and it's not the negative of that function. So that means that we don't have any symmetry. So let's just say this is not equal to f of x or minus f of x. And for our symmetry, we'll put none. Let's now look at asymptotes and end behavior. Because our function is a polynomial, we are not going to have any asymptotes. So let's put down a none for the asymptotes. And then for the end behavior, what we're going to do is we're going to find f at infinity and f at minus infinity. One thing that is really nice when we look at end behavior is when we have a polynomial, the end behavior is going to be solely dictated by what we call our leading term, which is x cubed in this function. So all we really have to do is look at x cubed. So we can say that f at infinity is approximately x cubed, which is infinity cubed. So we can say that our function, as x goes to infinity, is going to go to infinity. And then f at minus infinity is approximately x cubed, and this is minus infinity cubed, and we'll say this is minus infinity. So as x goes to minus infinity, our function is also going to go to minus infinity. Let's now look at the intervals where the function may be increasing or decreasing. I'm going to start by writing down our function because we're going to need that. F of x is equal to x cubed plus 6x squared plus 9x. To find where the function is increasing or decreasing, we need to find the first derivative. So f prime at x is 3x squared plus 12x plus 9, and we are going to set that equal to 0. We can factor out a 3, and we have x squared plus 4x plus 3. And we can factor this as x plus 3 and x plus 1. This gives us the solutions x is minus 3 and x is minus 1. We can now draw a number line. We'll label it x, and we're going to put these critical values on it, minus 3 and minus 1. And I'm going to put an f prime here just to remind ourselves that we are looking now at the value of f prime. So let's go ahead and let's highlight that. We can just look at the leading term, and that is 3x squared. So when x is in this region right here, our f prime is just going to be like x squared, and that is going to be positive. And then in our region to the right, it's also going to be positive. Now what we need to do is pick a point in between -3 and -1. I'm going to choose -2, so we're going to calculate f prime at -2. Looking up at the yellow function, this is 3 times -2 squared plus 12 times -2 plus 9. This is 3 times 4, which is 12, plus 9 is 21, minus 24. We don't care about the value. We just need to know if it's positive or negative. This is negative, so we're going to put a negative up here. And now let's add some increasing and decreasing lines. This is increasing, decreasing, and increasing. Let's write down that it is increasing on the region from -infinity to -3 and from -1 to infinity. Then we'll say that it's decreasing on the interval from -3 to -1. Let's now look at where our function may have a local max or min value. Based on the number line that we just drew, you can see that we are going to have a max at x is equal to -3 and then a min at x is equal to -1. So let's say we're going to have a max at x is equal to -3, and then we have to find what this maximum value is equal to. So I am going to go ahead and rewrite our function because we're going to need this. It is x cubed plus 6x squared plus 9x. Now we're going to find f at -3. -3 cubed is -27. And then we have 6 times -3 squared, which is 9, plus 9 times -3, which is -27. And this is equal to 0. So we can say that we have a local max equal to -3, 0. Now let's do the same thing for our local min. We are going to have a min at x is equal to -1. So we're going to calculate f at -1. This is going to be easier. This is -1 plus 6 minus 9, and this is equal to -4. So we have a local min equal to -1, -4. Now we just have one more item to calculate before we can throw all of this together on a graph. Let's look at the concavity and inflection points. When we find concavity, we need to find our second derivative. To find f double prime, I'm first going to put f and f prime up here. We're going to need f for the inflection point. F is x cubed plus 6x squared plus 9x, and we found that f prime was equal to 3x squared plus 12x plus 9. Now we can find f double prime. That is equal to 6x plus 12, and we're going to set that equal to 0, and that's going to give us that x is equal to -2. Just like we did for increasing, decreasing, let's go ahead and let's draw a number line. And we're going to put -2 on our number line, and then we're going to look at the value of f double prime. Let me highlight that. That is what we are looking at. If we have a point that is less than -2, we can say like -3, f double prime is negative. And then if we have a value greater than -2, like 0, it's going to be positive. So our function is going to be concave down in this region and concave up in this region. So let's write that it is concave down in the region from -infinity to -2, and then concave up in the region from -2 to infinity. Now we need to think about inflection points. An inflection point is where the concavity changes, and the concavity changes when x is equal to -2. So that is going to be our inflection point. Let's now find the y value of our inflection point. So we're going to calculate f at -2. Looking up here at our function that I highlighted in pink, we can find f at -2. So this is -2 cubed plus 6 times -2 squared plus 9 times -2. This is -8 plus 24 minus 18, and that gives us a value of -2. So we can say that our inflection point is the point -2, -2. Now we can go ahead and put all of this on our graph. Let's go back up to the top. I think the best thing to do is to first put all the points that we calculated on it. We found that we have an intercept at 0, 0. Let's go down here and see what else we found. We have a local max at -3, 0 and a local min at -1, -4. So our max is -3, 0. That's right here. We'll just put a little max here. And then our min is at -1, -4. That is right here. We'll label this min. And then our inflection point was -2, -2. So let's just put a little IP here for inflection point. Now let's go back and see what else we found. In part D, right here, we found that our function is going to be going to infinity when x goes to infinity and -infinity when x goes to -infinity. One thing we can do is just put a little line here and a line here to know which way our graph is going. Then we found that it is increasing as we get to -3 and then decreasing, and then at -1 it starts increasing again. So it's going to be increasing and then decreasing and then increasing. So we can actually go ahead and let's graph our function. It's going to come this way. We're going to go up to our max, and then it's going to be concave down till this point, and then the concavity changes, and it's going to be concave up, and it's going to pass through this point and continue going that way. Now let's go ahead and let's erase our other lines. And there we have our graph. We're now going to sketch the graph of a rational function. F of x is x squared divided by x squared plus 3. Just to make things easier, I already calculated the first derivative and the second derivative, so we can just focus on learning how to graph the function. Let's first look at the domain. We have to check if the denominator is equal to 0 because we have a rational function. X squared plus 3 cannot ever be equal to 0 because of the x squared term. So for the domain, it's going to be all values of x. So let's write down -infinity to infinity. Let's now look at intercepts. We're going to start by finding the y-intercept because that's easier. To find the y-intercept, we are going to let x be equal to 0. So looking up at our function that I highlighted in yellow, if we plug in x is 0, we get that f is also equal to 0. So this tells us that our intercept is 0, 0, and that is both our x and y intercept. Now let's think about symmetry. To find the symmetry, we need to calculate f at -x. So wherever we have an x in our function, we're going to plug in -x. This gives us a -x squared all divided by minus x squared plus 3. And this is x squared over x squared plus 3, which is the same as f of x. This tells us that our graph is going to have symmetry about the y-axis. Now let's look at the end behavior. I am going to go ahead and rewrite our function because we can't see it anymore. It is x squared all divided by x squared plus 3. When we look at asymptotes, we want to see where the denominator is equal to 0. In our function, it isn't, so we have no vertical asymptote. But now let's think about horizontal asymptotes. When you calculate a horizontal or a slant asymptote, you need to look at the highest power in your numerator and the highest power in the denominator. Those two powers are the same, so that tells us that we have a horizontal asymptote. And to find what that horizontal asymptote is, we have to think about the limit as x goes to plus or minus infinity. We're going to do this really informally. F of x is going to look like x squared over x squared, because only the leading terms count as x gets really big. And this is equal to 1. So we can say that our horizontal asymptote is y is equal to 1. Let's now look at intervals of increasing or decreasing. To find increasing or decreasing, we need to take the first derivative and set it equal to 0, or see where it's undefined. Our first derivative from up above was 6x all divided by x squared plus 3 quantity squared. It's never going to be undefined, but it is going to equal 0 when x is equal to 0. So if we set that equal to 0, we get that x is equal to 0. So we can go ahead and draw a number line, and we're going to put 0 on this, and we're going to look at f prime. We want to find if f prime is positive or negative. Notice that the denominator is positive, so we don't even have to think about that. We just have to look at the numerator. Let's pick a number less than 0, like -1, and we see that f prime is going to be negative, and then to the right, it's going to be positive. This tells us that our function is decreasing in this region and increasing in this region. We can say then that it is decreasing on the interval from -infinity to 0, and it's increasing on the interval from 0 to infinity. Let's now think about local max and mins. Looking up at part E, you can see that we are going to have a min when x is equal to 0. So let's go ahead and let's write that down. We are going to have a local min at x is equal to 0. And we saw when we were doing our intercepts that f at 0 was equal to 0. So we can say we have a local min at 0, 0. So that's just a min at the origin. And from our graph in part E, we can see that we have no local max. So let's write down no local max. Let's now look at concavity and inflection points. For the inflection point, we're going to need to find the value of f at a point. So let's go ahead and write down what f is again. F is x squared, all divided by x squared plus 3. To find concavity, we need to use the second derivative. So let's write down what that is. That was given up above, and it is 18 times 1 minus x squared, all divided by x squared plus 3 quantity cubed. We need to find where f double prime is equal to 0. So this is just where 1 minus x squared is equal to 0. And this gives us that x is plus or minus 1. Let's now go ahead and draw our number line. And now we're going to put 2 points on it, minus 1 and 1. And we are looking at the value of f double prime. Because our denominator is always positive, to find the value of f double prime, we really just have to look at this term right here and see if it's positive or negative. If we let x be in this region, say x is negative 2, then f double prime is going to be negative. In this region, we could say x is 0, so it's going to be positive. And then in our right region, if we say x is 2, it's going to be negative. This tells us that our function is then concave down, concave up, and concave down in those regions. Let's go ahead and let's write that down. It is concave down in the region from minus infinity to minus 1, and in the region from 1 to infinity, and then it's concave up in the region in between, which is minus 1 to 1. We are going to have an inflection point at negative 1 and at 1. I'm going to come up here and look at our function, f, and we need to find what it's equal to at minus 1 and 1. Because we have an x squared, it's going to be the same value for minus 1 and 1. So f at plus or minus 1 is going to be 1 over 4, so 1/4. So we're going to have 2 inflection points. The first one is minus 1, 1/4, and the second one is 1, 1/4. Now let's go ahead and put all this information on our graph. I think the best place to start is by putting all the points that we calculated and put those on our graph. We found that we have an intercept here at the origin. We have a local min there, and then we have inflection points at minus 1, 1/4 and 1, 1/4. So minus 1, 1/4 is right here, and 1, 1/4 is right here. Now let's see what else we can add to our graph. We have a horizontal asymptote at y is equal to 1. So let's go ahead and let's put that in. And let's keep in mind that our graph is symmetric about the y-axis. Now let's look at increasing, decreasing, and concavity. It is increasing on the right side of the graph and decreasing on the left. And then it is concave up in between the 2 inflection points. So we're going to have concave up and then concave down. And that's it. It really helps to calculate all of this information first, and then it's pretty easy to graph the function.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.